Please welcome to the stage MIT Alumni Association CEO, Whitney Espich. Good morning, everyone, and welcome to Technology Day 2025. To those alumni who are here for reunions, welcome home. I trust that your time back on campus is off to a wonderful start. Welcome also to family and friends and to other alumni in the room, and those of you streaming Tech Day live around the world. Let's all do a wave of hello. You are in for a taste of the MIT fire hose that I know you will find, as always, enlightening, motivating, and satisfying. This year's Tech Reunions and Tech Day are occurring alongside another significant milestone, the 150th anniversary of the founding of the MIT Alumni Association. Only 14, yes, let's applaud that. You're looking good for 150, right? Only 14 years younger than the Institute itself, the association has thrived for more than a century and a half. Today, our mission to connect our community of MIT alumni with one another and with the Institute remains as vibrant and vital in 2025 as it did back then in 1875. And there's one simple reason for that. Of course, it's all of you. It is your desire to show up for meaningful MIT traditions like reunions and like Tech Day, to stay connected with your peers, your classmates, your groups, and those who live in your region of the world, to give back through your philanthropic support for this amazing community that contributes its infinite gifts to the nation and the world. And I would add, it is because of your enthusiasm to keep active in what is happening at the Institute today, to learn about the bold ways that MIT is harnessing the collective talents of its students, faculty, and staff to keep society moving forward. Thank you. I have no doubt that you will leave today's Tech Day feeling as inspired and as proud of MIT as our alumni have been feeling since its very beginning. Later this morning, we will hear from MIT President Sally Kornbluth. But before that, we will go under the dome to learn about two research efforts that are foundational to MIT's national and global leadership. MIT HEALS, the MIT Health and Life Sciences Collaborative, and MYTHIC, the MIT Human Insights Collaborative. Before we get to that, a few quick housekeeping items. For those of you in Kresge right now, you can see a link on the screen that you can visit via your smartphones and tablets, and it will take you to a page where you can view today's full programming details. This is also the page where you'll be able to enter your questions when we get to that part of the program around MYTHIC and HEALS. And for those of you joining us online, you can add your questions too by putting them in the chat box below your video player. And for those who want to, you can upvote the questions that you find most interesting. Also, for those participating online, please note that closed captioning is available, which you can access by selecting the CC icon in the lower right corner of the video player. So I think we should be all set. And with that, I will say, enjoy Tech Day. Please welcome to the stage MIT Chief Innovation and Strategy Officer and Dean of the MIT School of Engineering, Anantha Chandrakasan.
Thank you very much, Whitney, and good morning. everyone. It is a pleasure to be with you here today. As MIT's inaugural Chief Innovation and Strategy Officer, I've had the privilege of working closely with faculty and staff across the Institute to advance President Kornblut's bold priorities through the development of cross-cutting initiatives. These initiatives leverage MIT's core strengths while opening new doors for collaboration across departments, across disciplines, and with industry and philanthropic partners to maximize real-world impact. MIT's alumni community has played a critical role in shaping and supporting these initiatives, and we look forward to deepening that engagement in the years ahead. Here, as you can see on the slide, you will see the major initiatives that have launched this past year or in development. Today, I am thrilled to highlight two of these institute-wide initiatives that I believe speak to the very heart of MIT's mission. The first is the MIT Health and Life Sciences Collaborative, or MIT HEALS. HEALS is an ambitious institute-wide response to some of the most urgent and complex challenges in human health today. The initiative brings together experts across MIT, from engineers and computer scientists to clinicians, biologists, chemists, and policy experts to develop transformative innovations in the health and life sciences area. And it does this by more than simply encouraging collaboration. It catalyzes it with targeted funding, institutional support, and an intentional focus on impact in key areas. HEALS brings our community together like never before. It supports students through UROPs and graduate fellowships, incorporates prestigious postdoctoral fellowships, supports faculty-led seed programs in key areas like women's health and neuroscience, and fosters deeper collaboration with industry and foundations. The initiative has already incubated several faculty-led programs, including a seed program for collaboration between researchers at MIT and Mass General Brigham, a pediatric innovation hub supported by the Hood Foundation, a fund to support much-needed research in menstruation science, and a program applying nano and microtechnology to health sciences. In just a moment, you will hear from some of our faculty about the groundbreaking work that HEALS was built to support. Angela Kohler, Professor of Biological Engineering and Faculty Director for HEALS, was planning to serve as a moderator for the Q&A portion with the speakers. Unfortunately, Angela has come down with laryngitis and has lost her voice. I will be stepping in to take her place after you've heard from our faculty speakers. But first, please enjoy this short video introducing MIT HEALS.
We're going to see some new technologies impact the world beyond anything we can imagine. And it's not just developing them in their own narrow lanes. We're at a point where we can juxtapose all these different technological approaches to make the whole greater than the sum of any of these technologies alone. I think we're really at the beginning of a whole new era of biological understanding, and one where I think MIT is really extremely well positioned to lead. The planet is changing, and new diseases are coming. The things that we thought we were treating our team all the time, which as inventors is an opportunity, but it's really a call to action.
Things that might have taken years in the past can be done in weeks, if not days, using the power of computation. And what better place to invest in technology than MIT?
At MIT, it's not simply the discovery that's up at the top of our ambition list. There's also applications of those discoveries to making the world better, to coming up with better products, better ways to do things.
One of the things that we're excited always to collaborate with our colleagues at MIT around is how do we make big leaps, how do we make daring departures from what is obvious and adjacent, and that's where many of the breakthroughs come from.
We want to find a mechanism to bring people from lots of different areas together so we can get this synergistic effect to solve really important problems.
There's been a natural confluence of the science, the medicine, the capital, and the entrepreneurs. And that doesn't exist anywhere else in the world. And MIT has been vocal to that.
Being in this environment allows us then to tie into that ecosystem and to learn from them in terms of understanding how best the work we do can be applied outside. But vice versa, it allows them to have access to how we're thinking about pushing the boundaries of the future. And so that's one of the many reasons that we are launching MIT Feelings.
Anyone who has spent any time at MIT knows this place has a secret sauce. And I love so much that we can now combine that with the strength of the hospitals, with all of the remarkable industry connections in Kendall Square to really move health and life sciences forward in ways that we can only imagine.
Please welcome to the stage Professor Angela Belcher.
Good morning. It's wonderful to be here at Tech Day and Reunion. This is one of my favorite venues to speak because this is such an amazing audience of brilliant people. Today I want to share a story, a mission. Hopefully my slides will start. A story, a mission around changing the optics of ovarian cancer. So I hope today, in this short time we have together, to share 3 points with you. Well, I hope that one of the points will surprise you. I hope that one of the points will cause you pause. And I hope the third point will give you hope. But I'm not going to start with ovarian cancer. I'm going to start with an asteroid. I'm going to start with a story about an asteroid Bennu that you might have heard about. So in 2020, NASA landed a probe on asteroid Bennu, which is traveling at a small asteroid, traveling very fast. The Earth is also moving. But amazingly, scientists and engineers figured out a way to study this asteroid, land on it, collect rocks or specimens, bring them back to Earth and study them. It was an incredible feat. It was a big group of NASA engineers that did that. And they even actually have images, near-IR images and other kinds of images of landing and collecting it. And yet, in 2025, we still don't have a way of accurately looking this deep inside a woman's abdomen to find a tiny tumor for ovarian cancer. So we think this is unacceptable. Does anyone in this room think it's impossible to look this far in a woman's abdomen and find a tumor? We don't. We think it's completely possible, and that's our mission. So one woman is diagnosed with stage 3 or stage 4 ovarian cancer every 3 minutes. This is about the same time it takes to toast and butter your bagel. And the 5-year survival rate for stage 3 or stage 4 is pretty terrible. Stage 4 is 17% and hasn't improved in 20 years. Currently, there is no method of screening, and we know that things that have been looked at for screening do not increase survival rate. A recent study confirmed that when a woman has her fallopian tubes taken out, especially at high risk, there's almost no cases of ovarian cancer. So we know that removing the fallopian tubes reduces or prevents ovarian cancer. So this is what I consider the very surprising point, is that we now know that 85% of ovarian cancer does not come from the ovaries. It comes from the fallopian tubes. It's really fallopian tube cancer. We know that in the fallopian tubes, actually I have a model of fallopian tube right here. In the fallopian tube, which is connects between the uterus and the ovaries, that very small mutations called P53 mutations start in the fallopian tube and they develop into precancer lesions. They can stay as these precancer lesions for up to 9 years before they start to spread. And when they spread to the ovaries and they spread through the whole intracranial cavity of this abdominal space. And that's one reason it's such a deadly disease and it's so difficult to treat and cure. Because it's not one tumor, it's tens or hundreds of tumors in this space. And so basically I was on a Zoom a couple of years ago now when I was listening to Professor Becky Stone, a gynecological oncologist at Johns Hopkins, who said when a woman has her fallopian tubes taken out, they embed them in wax and cut them into small sections to look for any precancer lesions. And she said it's like finding a needle in a haystack. So I direct messaged her, I didn't know her, and I said, we can solve that at MIT. We can develop a system to rapidly scan through the fallopian tube to find these precancer lesions. So we set about to do that. Now we have a goal in the next 5 to 10 years of being able to diagnose and treat ovarian cancer at stage 0 or stage 1, and ultimately want to be able to prevent ovarian cancer. So I have many co-pilots on this journey, which are here. These are my collaborators in the School of Engineering, and my collaborator, Becky Stone at Johns Hopkins, and our amazing students and postdocs. So we use some of the same technology that's used for looking at BenU, and we're looking at it for understanding early lesions in ovarian cancer. We're using hyperspectral imaging in near-IR 1 and 2. We developed the system very rapidly in our lab. And so people will tell me, wait, fallopian tubes are so hard to see. They're invisible. You can't see them by contrast and enhanced CT. You can't see them by X-ray or ultrasound, but they're not invisible. You just have to know how to look at them. You have to be able to look at them at the right wavelength of excitation and emission, and we can do that. And so when a woman has her fallopian tubes taken out, now at Johns Hopkins, it takes 5 minutes, and the samples are shipped to MIT where they're logged, they're imaged, and we start to study them. So every specimen is logged. We look at them at white light. We're collecting the largest sample of these fresh fallopian tubes. We use our imaging, we use AI and ML, and we look for precancer lesions. So then we actually mark them. We send them back to Johns Hopkins where they undergo regular pathology, and we can find very rapidly changes in the fallopian tube that are less than 200 microns in size that wouldn't be seen any other way, and we can mark those. Now we're working with, we can look at the differences between patients with different kinds of genetic mutations or other kinds of disorders and compare them. So we're collecting a lot of data. And then we're using our data and AI and ML to be able to try to find these just with light, how the different fallopian tubes interact with light to find these precancer lesions. And we're working with Professor Chandrakesan on this, and we're at an accuracy about 85% right now on our first 45 patients. We're also able to collect cells from these and build patient-specific cell lines and patient-specific organoids, which we can study different treatments and try to understand from these fresh samples what kinds of therapeutics could be patient-specific for intervening and preventing ovarian cancer. We also are working on blood markers and urine markers, new kinds of nanotherapeutics for this, vaccines, organ on a chip, and ways of understanding the biology in the first events in ovarian cancer. We're also doing hardware and chip design for machine learning, whole organ, whole tissue segmentation, so we can do real-time machine learning in handheld devices that could be used in the clinic. So ultimately, we'd like women to be screened for ovarian cancer at the same time they come in for, say, a mammogram. We're all in to solve ovarian cancer. We're doing this for all the women that are affected by the disease, and so many women that you may know that had so much more to give to this world, but didn't have the opportunity. Thank you for your attention. We have many other asteroids we're chasing in my lab. I have an amazing group of graduate students and postdocs and future alums out in the lobby who can take you through some of the data that I showed you today and show you some other things that we're doing in the lab. Thank you so much for your attention. Thank you for being here and continue to be a part of our community. Sorry, get your MIT periodic table outside.
Please welcome to the stage Professor Jonathan Gruber.
I don't have nearly as cool stuff to show you. I'm sorry. I don't have cool graphs and things like that. I'm just going to talk. And I'm going to talk about how we pay for all this. We are on the edge of amazing discoveries. Many pioneered here at MIT, like Angela just discussed. But I'm from the dismal science, economics. I'm here to tell you we have to pay for it. How do we do that? Well, I think the first step is to recognize that risk sharing of medical costs is critical. Medical risks are the greatest financial risks facing most Americans. They're difficult to prepare for, and they're large and unexpected. So what do? We have something called insurance, which spreads that risk. The idea is we prepay an amount. We all think it's too much, but we prepay some amount. And in return, when we get sick, our medical bills are paid. That's one side of the equation. The other side of the equation is life science is very expensive. New innovations in life science are miraculous and be miraculously expensive. Estimates suggest that the cost of developing a new drug is about $2 billion, and that results in high price to end users. But the results are miraculous. Let's look at two examples. One is GLP-1s, like Ozempic. Here is a drug which appears to miraculously have enormous benefits in terms of weight loss, in terms of cardiac health, and other things. It looks like an incredible development. It's $1,000 a month, and you got to take it forever. Or let's talk about an incredibly expensive miracle: cell and gene therapies. There's a truly horrific disease called spinal muscular atrophy. Kids are born with, they live horrible existences, they're dead at a young age. You can't imagine anything sadder. We've cured it. There's a genetic cure which basically goes into the body and reprograms the genes to get rid of this disease. It's a miracle. Kids who would have died at 2 may live normal, regular lives. It's $2.1 million. Now, these costs are unpayable without insurance. Okay? There's no way we can ask people to paying these costs without insurance. But insurance in the United States is very incomplete. And there's 3 kinds of holes in insurance in the US. The first is discrimination. And this is a problem that's getting worse. The more insurers know about you, the more they can avoid sick people. And it's increasingly, our genes can tell our life patterns of health. If insurers can have that data, which they can ultimately have, that will mean they will not want to insure the sickest people. Indeed, in the limit, with perfect information, there's no more insurance. Once it insures everything about you, they're going to say, look, you're going to cost me X million dollars, pay me X million dollars, or I won't insure you. Now, the Affordable Care Act, which I was proud to help President Obama develop, banned discrimination in insurance markets. And so we have, for the time being, addressed that problem. Public policy being what it is, that's not necessarily a solution that will always be there. It's something to be vigilant about, but it was a critical accomplishment of this law. No more is America a nation where one bad gene or one bad traffic accident can result in bankruptcy. But we didn't do it all. There's still 25 million uninsured Americans who cannot afford these treatments. And we have multi-payer health insurance, where individuals move across payers. And as a result, insurers don't want to pay for an expensive curative therapy. Insurers want to pay $2.1 million to cure you, when 2 years later you'll be with some other insurer. So let's talk about cell and gene therapy. Adoption has been very slow because insurers are wary of covering cell and gene therapy. They don't want to pay these large costs if people are going to leave. And they're worried that these things may not work a long time. So when They do cover these therapies. They fight to limit coverage, but people can't afford it without insurance. These are miraculous drugs. These are incredible life savings opportunities. And the fact that insurers aren't covering them is starting to feed back into drug development. The drug companies are someone in it for the social good, but they got to make a buck too. And they don't want to develop a drug that people aren't going to buy. And as a result, if you have a therapy that insurers are not going to cover or discriminate against, it's not going to be developed. So what do? Well, we could have a single payer healthcare system. We could talk about that. You can watch my we can all have a nice long conversation about that. You can watch my TED lecture online where I talk about that. But while that's hard politically, we actually have an example of single payer we don't talk about in America, which is for renal failure. For people whose kidneys are failed in America, we have a single payer healthcare system. The Medicare program has an end-stage renal disease program, which is a single payer healthcare system. We could do this for genetic abnormality. For people who've lost the genetic lottery, who are born with these horrible genetic diseases, we could set up a single payer system. And that would be just like we've done for kidney disease. And that would be a way to share the costs. We could also rely on the private sector, try to spread the costs, but that is going to be trickier and has not really worked so far. So we need some kind of intervention to think about how we can address these holes in insurance. Now, what about pricing? $2.1 million seems like a lot of money. What do we do about that? Well, the traditional approach around the world, but not the US, is to regulate healthcare prices based on what we call their qualities, quality adjusted life years saved by the medical. So if a medical intervention is very effective in saving you years of life and life in high health quality adjusted, it's worth more. So basically the idea in the rest of the world is that they measure what medical services should be reimbursed based on what they're worth. Sounds pretty sensible to me. Not clear why we don't do this in the US, absent politics. Seems pretty sensible. We should reimburse medical services based on the value they deliver. This has been a great solution for the rest of the world so far because they've managed to find drugs and services which are overpriced, lower their price because they're not worth it. This doesn't solve the problem with cell and gene therapy because guess what? $2.1 million is a bargain. To save a kid's life, that's worth it. And so now we have a real difficult problem ahead of us, which is how do we deal with incredibly expensive and incredibly effective treatments? This is going to be a real challenge. It's going to be a challenge facing our society. We can talk about regulation of prices, but there's a risk here. And the risk is, what about innovation? And the drug companies, if you talk about drug price regulation, I'm going to go over by 1 minute. If you talk about drug price innovation, okay, they'll say, oh, if you regulate our prices, we won't innovate. But guess what? We can have our cake and eat it too. As I point out in my book, Jumpstarting America, with my Nobel Prize winning co-author Simon Johnson, one of many Nobel Prizes in economics and economics adjacent fields in the last decade. Economics has won more Nobel Prizes in the last decade than the rest of MIT combined. Just saying. We describe the key role that public research and development plays in innovation. In 1965, 2% of our entire economy, 2%, one in every $50, was government-sponsored science. Today, it's less than 0.5%. It's falling rapidly. In the latest budget from the Trump administration, for many major funding organizations, it's cut in half. Okay? Public R&D is the growth secret to America. It complements private R&D. When there's more government R&D, there's more private R&D. Every dollar of NIH funding leads to $8 of private biomedical funding. Okay, there's huge economic returns. Every dollar of NIH funding leads to $3 in stock market value. Yet these investments have been falling. I was proud to work with President Biden on the CHIPS and Science Act, where we made a little bit of a detour. That is now we're heading back in the other direction. So at the end of the day, what we need is we need to recognize society is going to have to share the cost of these miraculous inventions. We want them to keep going. We want the science and stuff that Angela and others will describe to keep going. The way to do it is to have the government come in, recommit to financing innovation, and then it's society commit to covering the risks for those of us who are most vulnerable. Thank you very much.
Please welcome to the stage Professor Hugh Burr.
Good day. I'm honored to be here. As a young man, I was inspired by Leonardo da Vinci. Da Vinci worked in the 15th century, operating at the nexus between engineering science and biological observation, producing devices that would inspire for generations. Here you see a winged device inspired by keen observations of flight, biological flight. As a young man, I was inspired by Da Vinci in my rehabilitation process. Both of my legs were amputated in a mountain climbing accident from frostbite. And after my amputations with my new body, I asked myself, what next? I wanted to return to my chosen sport of mountain climbing. But how? Inspired by Da Vinci, I looked into nature. What's a great mountain climber? The mountain goat. I looked at the hoof, I studied it, and developed a hoof-like climbing appendage. High drummer that enabled me to stand on small rock edges the width of a coin. I was also inspired by the giraffe that reached towering heights. Given that I'm a bilateral amputee, I'm able to adjust my height. Here I'm a towering 3 meters high, able to reach hand and footholds that no one else can reach on planet Earth, to the chagrin of my competitors. So by operating at this nexus between engineering and biology, I was able to design my own climbing legs that enabled me to climb at a more advanced level after the accident than I had achieved before the accident. And I realized through this experience that technology has the power to heal, to extend human capability beyond innate physiological levels. Today I'm an MIT professor, and I'm wearing these bionic limbs that were devised in my laboratory. They comprise muscle-like actuators, sensing and computation. They enable me to walk normally, and as I stated earlier, to return to mountain climbing. But they're not so sophisticated that they're linked to my brain. They're not linked to my muscles and nerves. I can't think and have agency over them, nor can I feel them and have ownership. That is a key mission of the new Kaylee C. Yang Center for Bionics, for which I co-direct with Professor Edward Boyden. So here you see work produced by the center. This is the first bionic leg in history that restores natural gait, wherein the limb is completely under the control of the peripheral nervous system. So all these nuanced motions that you see and the torque outputs are actually being mediated by spinal circuits in the brain, not by robotic algorithms. We're also applying this to the above knee case. Here's a person with transfemoral amputation manipulating a ball with great agility. We've also applied these neural interfacing strategies to the upper extremity. Here's a box and blocks exercise, showing the ability to grasp and move objects. The center is also developing powerful exoskeletons that augment the physicality of persons with intact limbs, enabling people to jump higher, run faster through tremendously adaptive control systems. And finally, the center is developing ways of using computation and artificial stimulation of muscle to restore natural movements for persons, for example, with spinal cord injury. So on being bionic, what does it mean to be bionic? What does it mean to have one's physiology so beautifully fused with electromechanics? We have human experimental subjects, of course, that come into the laboratory. And during these sessions, we link our designed bionics to their peripheral nervous system. So they not only have agency, they not only can think and directly control the motors, they can actually feel the synthetic limb in terms of proprioception, cutaneous touch. When we make that link, people say remarkable things. One subject says, this one is alive. My other one, the passive low-tech one, is not. The device is made of titanium and aluminum, carbon, and so on. Not a biological element in the bionic limb. But because it's linked to the brain, it becomes alive, it's embodied. The subjects, because of this, do remarkable things. After a session one day, the experimental subject was chit-chatting about his life, chatting about his wife and his kids, and he's gesturing through the bionics. Naturally, you don't see this with a regular, just robotically controlled device. This is extraordinary. We're taking this a step further and asking the neuroscience question. Can the human nervous system deeply embody a non-anthropomorphic structure like horns or an octopus limb? So with artist Anna Reichovik, we're doing this work. We're actually building a robotic octopus limb and attaching it to the human nervous system and asking the neuroscience question, can the human brain completely embody something that's non-human? If our data support our hypothesis, I believe in 100 years, human morphology and dynamics will be unrecognizable from what we are today. So I'll finish up with a video that captures the extraordinary power of bionics to change lives. Bionics has changed my life. These mechatronics that I'm using here enable natural movement. I can run, I can climb mountains again. This video shows a lady that was just fitted with bionics and her emotional response.
Oh my God. Oh my God, I can't believe it. It's just like I've got a real leg. I don't start running.
Now turn around, do the same thing walking up. Walk up, get on your heel to toe, like we normally just walk on level ground, try to walk right up.
Oh my God. Oh.
Pushing you up.
Yes, I'm not even, I can't even describe it.
On being bionic, she cannot describe it. The integration of electromechanics with humanity makes for extraordinary results. Thank you so much.
Please welcome to the stage Professor Brian Bryson.
Good morning. So tuberculosis is an ancient problem, but the disease is still here today. When I think about this problem, it's important to recognize that this is a problem that's been around with us for millennia. But what I'm here to tell you is about the solutions we're implementing today to make this a true problem of history. So pictured here are 2,000 silhouettes, more than the occupancy of this room. Now, what I want you to do is multiply this number by 2. That is the number of people who will die today from tuberculosis, and tomorrow, and the next day. Now, let's multiply this number by 1 million. And that's the number of people estimated to currently have been infected with the bacteria. Okay? Now, for those of them who are still infected, if their immune system begins to fail, they could be part of the next 4,000 without more effective intervention. Now, when we think about this, this is not a problem in faraway places. It's happening in Kansas. It's happening in South Carolina. It's happening right here in Massachusetts, right in Boston. TB is still a problem today. This is the leading infectious disease killer in the world. TB is not a problem just in our history. This is something not just about mummies. This is about mothers.
students, and workers all getting infected today. So the WHO actually estimates that in the next 25 years, there'll be more than $1 trillion in economic losses due to TB. This is the cost of inaction. So here at MIT, we are approaching this problem with urgency and intensity. And I'm here to invite you on our mission to end TB. Okay, so what does that look like? All right, so we actually have only one vaccine currently clinically approved for TB. This vaccine is 100 years old, okay? Now this vaccine has not been able to end the TB pandemic. Okay? So now we're at MIT. If somebody comes to tell you that we've got a 100-year-old technology that doesn't work the way that you want it to, you say, let's build a better one, right? Okay, so that's what we're gonna do. We're gonna build a better TB vaccine. So what does that look like? Okay, so when you're building a vaccine, it's a very simple premise. What you're hoping to do is engineer the immune system to deal with the pathogens like bacteria and viruses that can cause human disease. All right, so that's our goal. Okay, so what we are doing is we are going to war with these pathogens. That's what the immune system is doing. We're trying to equip the immune system to be able to do this. Now, what does that look like? If you're going to go to war with a pathogen, you really need to understand your enemy. You need to understand its tricks. You need to understand the offense and the defense intimately. Okay? Think about it this way. Are you going to show up to a sword fight with a spoon and expect to win? Right? Come on. Right? What we need to be able to do is equip the immune system with precision in order to have the upper hand against these pathogens. Okay, so imagine this. What if we could figure out of the 4,000 weapons that TB could deploy, what if we could pre-equip the immune system to be ready specifically for the ones we know it's going to deploy, right? So that was our goal. That was our dream, to be able to engineer the immune system with such precision that we would really know what are the proteins to go after. That's the key of building a better vaccine. All right, so why is this hard? Okay, this is really hard because during infection, there's actually not a lot of TB around. As Angie mentioned, we have to solve a needle in a haystack problem, okay? So each one of these gray circles here is a human protein, and the sole green protein circle here is a TB protein. So what our lab did is we built next generation measurement technologies to really go and find the needle in the haystack, to go and identify the TB proteins that are really important to put into a vaccine so you can make sure and ensure the immune system is poised for those small number of weapons that the bacterium is going to deploy. And this is actually really important because many of the proteins that we identified were the ones that people have not put in vaccines in the past. All right, problem number 2. Vaccine trials are incredibly costly and super slow. So we said, what if we could instead build what we call patient avatars? Imagine this. What if you could just give a blood donation? One of the most least risky and most commonly performed medical procedures. And if we could then take that blood sample and then test a bunch of different vaccine designs and figure out which is the one that's really going to work for you. Okay. So that's in fact what we did. We said, let's use our new measurement technologies and go ahead and test a bunch of different vaccine concepts. Let's do that, right? And then we can, with that blood donation, test hundreds of vaccines, which you could never test in a single individual or in a single vaccine trial. Okay, and why is this important? So if you look here at the graph on the right, this is a TB vaccine design that you would design based off of our observations, based off what the textbook would tell you about immunology. That's the textbook design response. But we had this moonshot idea. That's design 2, which is what the textbook would tell you not to design. They wouldn't tell you to think about this. But because we have these technologies that allowed us to test a bunch of different vaccine designs, what I hope you can see is that design 2 is 1,000 times better. So now what we can do is we can say, let's go with that vaccine design. This is really important because if we didn't have these measurements, we wouldn't have the opportunity to actually challenge the dogma and put a new opportunity in front of us in terms of what vaccines we could design. So this is really amazing for TB But it's not just about TB. This is about rewriting the vaccine development playbook. The old playbook would say, you should do this all in mice because they're easier. You should do this in human because there's not a lot of, and if you're going to do this in human, do it in a pretty homogeneous population. And why don't you just, instead of building new technologies, test each 4,000 proteins one at a time? But even if you do that, one protein a day, that'd be 10 years, and that's too long. So we said, let's rewrite the script. Let's do this all in humans. And if we're going to do it in humans, let's do it in as genetically diverse of a population as possible because this is a global problem. And why don't we just build the right technology so that we can pick the right things in the first place? So I want to leave you with this. The red curve is the status quo. The y-axis is mortality per million. So this is TB mortality. The dark blue curve is what would happen if we had a 60% effective TB vaccine. And what I hope you can see is this would allow us to change history. So I'll ask you again, please join us. If you're a protein geek, we've got problems for you to solve. If you want tough machine learning problems, this is one. If you want to think about implementation, we've got problems for you as well. Let's go do this. Thank you.
Please welcome back to the stage MIT Chief Innovation and Strategy Officer and Dean of the MIT School of Engineering, Anantha Chandrakasan.
First of all, thank you all for that amazing set of presentations and truly impactful work. We have a large number of questions, and we're going to get through as many as we can. And there were a number of questions related to funding and federal funding and foundation funding and so on. So we're going to broaden this and just ask, how is funding impacting research discovery, and what is the best way to support your work right now? So why don't we start down the line, start with Angie.
Okay, well, thank you for that question. I think that we're trying to adjust to changes in federal funding. And it does definitely means shrinking our lab, at least in my lab, in a time that the knowledge is expanding and we want to run faster. So that is it's very stressful. I've been a professor for 23 years, and I've never been in a situation like this before. I'm very fortunate to have foundation funding and private donation funds, which is allowing us to think and move quickly. You said the best kind of funding. So I'm an engineer. The co-pilots I showed you on my project are engineers. We're thinking, solving problems all the time, inventing. We're inventing every day. And having funding that allows you to come up with an idea, run with it quickly, which is not government funding, is the most valuable kind of funding, and it leads for us to the clinic and translation faster.
Yeah, I want to emphasize. I'm the fake scientist here. So let me just emphasize 2 points. Point one is that the funding is not just about inventing cool stuff. It's about training the next generation of scientists. Okay, the next generation of scientists learns what they really need to know in the lab. And when we cut funding, we don't just not get the next generation of bionics or ovarian cancer treatment. We don't get the next generation of scientists. That's one point I want to make. The other point I want to make is I want to come back to the economics, which is this is the best investment society can make in our future growth. Everything that you're using technologically today, from your phones to your drugs to the GPS to the planes you fly into your computing, all came out of government-funded and also philanthropically funded basic science. We will not feel the costs. We will not feel the costs and pain of this for many years, but when we do, it's going to be disastrous. And I think we all need to recognize that science funding isn't just about having cool stuff. It's about our remaining economically vibrant nation. Thank you.
Yeah, at the center of Bionics, we're not limited by ideas of what direction we should move. We know where to go. We know the pathway to rapid innovation. What limits us often is funding. So I can echo my colleagues' statement. It's critically important. Of course, not only for rapid innovation and creating the future's new industries, but also, as stated, in developing the next generation of minds, next generation of scientists. It's never been so important, given the rapid shrinking of research funding from the US government. Foundation and philanthropic ones have never been so critical. I mentioned the K. Lisa Yang Center for Robotics. Lisa Yang is a wonderful person, very generous philanthropist with an incredible vision. So we're very fortunate to have such minds.
Yeah, so I share the sentiments of everybody on the stage, but I'll talk to you from like the real life perspective of having a grant cut. So we were a part of a real big TB moonshot, and then all of a sudden the money was gone. The next day we got a stop work order, and that was terrifying because I just got tenure, but working as a junior faculty member, you're kind of on this cusp where you're trying to do everything in your imagination, in your wildest dreams, and you're full steam ahead. And then all of a sudden, you're trying to anticipate everything that could possibly go wrong. But when you get a grant, you don't expect it to be gone the next day. You expect to have some runway. And the fact that there are these now concepts of disappearing runways is really disastrous for science. So I think we really need to think about how to design the next generation of runways so that people will have the ability to train the next generation of scientists to keep innovative ideas alive. Because otherwise, if we can't create multiple different runways, I don't know how we survive.
Got it. Question for all, but maybe Brian, you particularly, is there any research undertaken at the Harvard MIT MD PhD program connected to the research and researchers featured today?
Yeah, absolutely. So we've had the great pleasure. So my lab is located in the Reagan Institute, which is one of the newest buildings on campus. And we have tons of MD PhD students from the Harvard MIT PhD program. And they've worked on any number of different topics in our building. I know of MD PhD students who are working on new questions in women's health. We've had students in our lab working on how to build new machine learning models for thinking about vaccine design. So yeah, their hands are making an impact, but they're not just making an impact in the laboratory, they're helping in the classroom as well. I teach a class that has about 50% MD PhD students, and they've been really strong contributors there as well.
Anyone else want to add to this?
Yeah, sure. So many of the interesting problems and solutions to those problems occur at the intersections between established disciplines. So it's because of that, it's critically important that we train minds to think across disciplines. So in my lab, I have several students that are pursuing a PhD in engineering at MIT, and they're also pursuing a clinical MD capacity. And that integration of having clinical knowledge, deep knowledge of the biology and patient needs with deep knowledge in engineering, that is very powerful for innovation.
This is really what EELS is about, is bringing different disciplines together. So it's great that we're also training this next generation of students to think this way. So that's amazing. Angie, we have a question for you. Are there identifiable biomarkers for fallopian tube lesions or tumors?
Yeah, that's a great question. And so I didn't go into all the details in my talk, but there's two main ways we're looking for these precancer lesions. One are with nanoparticles that we make with Paula Hammond that have antibodies to known markers. One is called LAMP-C that is known to be expressed in some of these early ovarian cancer lesions. But as we go in and we're learning more about them and collecting live cells with Kripa Varanasi's group and working with Sangeeta Bhatia, we're hoping to find new biomarkers. But you and I are working on new optical biomarkers together, where I didn't show this example before, and my students are upset about that. So This is what green light looks like going through the skin, and this is what red light, I don't know if you can see it, this bright light looks like. And as you go further into the infrared, you can see deeper and deeper. We're looking together, Anant and I are looking together for new optical signatures that will differentiate an early lesion from a non-lesion, and using ML to be able to predict that. So there are some known, they're not perfect. We're looking for more. But we're also looking for optical and physical biomarkers as well.
And just staying on this topic of AI and ML, I mean, many of you are actually creating the data itself, right? There's so little data. Could you talk a little bit about the role of machine learning and AI in your respective research areas?
Sure, I can take a start. So, you know, one of the things amazing about biology is biology really offers a kind of unique glimpse at machine learning problems, because oftentimes, if you think about the number of clicks that somebody might do in an Amazon shopping cart relative to the number of experiments we can do in a week, it's vastly different. So even when we think about the machine learning models that we use to predict what should go next in your shopping cart versus how you might predict how the next vaccine should be designed, the computational approaches are very different. So what's amazing about being at this interface of biology and machine learning is that we actually get to like push new frontiers and create new questions for the machine learning experts to think about asking. So there's a really great opportunity, because I think biology has brought new questions and problems for machine learning experts to work on in ways that they wouldn't think about if they were working with other data sets. So that's really amazing.
I'll just add to that so in the past, the field has had challenges modeling with high fidelity human dynamics and all its complexity. We can model the simpler machine, but in the goal of understanding human machine interaction dynamics, that's been challenging. So this explosion in AI is really opening up the door to creating for every person what I call a digital avatar, where we can, amputate the limb of that avatar, put a prosthesis of a particular design, and then using with very rapid computers and AI, rapidly iterating the electromechanics, the control system, how it's linked to the nervous system, to optimize and deeply personalize the interaction with an individual.
Yeah, I mean, I think, let me once again play the dismal science role. We're all worried about the robots taking over, right? We're all worried about AI, the negative effects of Gen AI. And this is something that economics is thinking a lot about. In particular, my colleague Doron Asimoglu and David Otter are working on issues of how AI is going to affect the future of how we all work. And I think they have this wonderful concept of sort of labor substituting AI and labor complementing AI. What does that mean? That means, is AI going to be like automatic checkout at the grocery store, which just sucks? Or is it going to be like this, which is complementing and making us more productive? Okay. Is AI going to be the tools that help promote discovery, the tools that help us move forward as a society, the tools that replace us as a society? This is actually a choice. Doron Asimoglu, Simon Johnson, who recently shared the Nobel Prize, have a wonderful book called Power and Progress, which is all about the choice we face in where the future of technologies like AI take us. And I think we are not passive passengers on the ship that is developing AI. We are active participants, both as scientists and as citizens, in terms of thinking about where it's going to take us and the role we're going to play. And I think we all need to be paying attention to this and making sure that society is paying attention to how AI is used and shaped in the future. Yeah.
Oh, was it my turn? So I was going to say that it's critical for us. One of the going back to fallopian tube cancer, these small cancer lesions. There's not enough data about these small cancer lesions because they're pretty much invisible. They usually get thrown away and they haven't been studied. And so that's one of the things that we're doing is working so hard on collecting that data. And I just wanted to point out that it's through HEALS that Anant and I have forged this collaboration on how to use AI to pull out meaningful information from relatively small amount of data. But they're both so important, and the interface between them, and having our shared postdocs and graduate students being deep thinkers in both areas is really critical.
Really is, opening up new kinds of education. Really, our students are thinking across domains. I think this is really important. Come back to Professor Gruber. What are the main economic and policy barriers to implementing federally regulated, tax-funded universal healthcare in the US? Simple question, and you have about a minute to.
The joke that's told about this is that the health economist dies and goes to heaven, and God says, when she gets there, you can ask me one question. She says, well, will we ever get single payer healthcare in the US? And God says, yes, but not in my lifetime. Look, the barriers are purely political, and they're quickly three. Barrier one is we finance healthcare through a hidden tax in America. So MIT gives me healthcare. It costs MIT about $15,000 a year to insure my family. They don't just do that at the goodness of their heart. They pay me $15,000 a year less. That's the way the labor contract works. Our wages are lower because we have health insurance. If you move to single payer, you're going to get $15,000 raise, but you're going to pay $15,000 more in taxes. Now, as an economist, I'm like, whatever. You're in the same spot. As a voter, you're like, well, wait a second. I see the taxes. I don't trust someone to get the raise. So that's barrier one. Barrier two to this is that basically, while we all complain, 90% of Americans have insurance that largely functions. And we're a society that sort of buys the status quo. And we're not that excited to give up something that largely functions or something we don't know about. So it's hard to get people to give up what they like, or at least don't dislike too much, something they don't know about. And barrier three is just political economy 101. The U.S. health insurance industry is a $1.2 trillion industry. They're not going to say, hey, it's been a good run. We're out. You guys have fun. They're going to fight. And they're going to spend $1.2 trillion fighting. And that's a fight the government doesn't often win. So I think it's really just until someone, I'm not saying single payers are going to happen. I'm saying it's a bad idea. I'm just saying people are too glib. And until we have a plan for overcoming those three barriers, it's not going to happen.
A question for you. Could you talk a bit more about how bionics are evolving beyond prosthetics and what opportunities this opens up for future collaborations across MIT?
Yeah, half of my research group is focused on permanent assistive devices. The other half is focused on wearable robotics that augment humans beyond innate physiological levels. So I mentioned in my remarks earlier about exoskeletons. We've actually shown that we can put a robot on a human with intact limbs, and they're able to walk with less metabolic energy, lower musculoskeletal stress. We've been able to show we can augment jumping, running speed, and so forth. And we're actually working on a bionic shoe. I was part of a MIT startup called Defy, co-founded with Luke Mooney. And we're actually envisioning the future of apparel and shoes. So imagine a world in which shoes power your every move. That's going to happen very, very soon. And I predict when we're successful, we'll all look back and say, remember when shoes didn't do anything? So the experience of being at the airport, hitting the moving walkway, and then leaving the walkway, saying, wow, walking is slow and cumbersome. We've built that capability into a shoe. So that's just one particular technology that's coming down the pike that'll be massively disruptive.
Amazing. Thank you. Brian, what lessons from your TB research could inform modern disease prevention or our response to emerging infectious diseases more broadly?
So that's a really good question. I think that what these studies have taught us is that we have a really great suite of measurement tools to make us really positioned to deal with emerging infectious diseases. So all the technologies that we've used in our lab are not custom built specifically for TB. So when I think about the next emerging infectious disease, I think that we have a suite of amazing tools that can really help us quickly identify what are sites of vulnerability, what are the proteins that should go in a vaccine, how much do we need to worry about variation, mutation, evolution when we design these ideas. So, we focused on TB because to me, I'm like, well, this is problem number one in infectious disease. But the tools that we've developed are pretty generalizable. So I think we're really equipped. Hopefully we don't see that anytime soon for whatever emerging infectious diseases come out of.
Great. So a question for all of you. How can these discoveries be made accessible to the broader public? For example, ensuring mobility aids reach the growing elderly population. But think about it more broadly. How can we and this could include startups as well, and how do we get this to scale?
I mean, let me start. I think it comes with two things. One is we have to fund science. I mean, you look at the incredible stuff on this stage. I mean, TB, mobility, ovarian cancer, these are incredible things folks are working on. We have to, as a society, commit to using science to solve our biggest problems. That's step one. And step two, we have to recognize that we need to share the risk between the more fortunate and the less fortunate. Okay? Basically, many of us are blessed with incredible luck. We're all hardworking and skilled, but let's be honest, we've had good luck in many ways, and we need to share the residue of that luck with people who haven't had such good luck, who were born with TB, who are in terrible accidents, who have ovarian cancer. And the way we do that is by making sure that society funds those innovations and shares the cost of paying for them. Any other?
Yeah, I'll just jump in. So we for decades, I thought carefully about how to go from bench to bedside as fast as possible. And critical to that is in the very beginning of the design cycle, all critical stakeholders need to be in the room. So the patient, the design engineers, the clinicians, and so forth, reimbursement experts, regulatory experts, and so on. So that initial design premise is actually correct and has legs, pun intended, and can rapidly translate to the market. We also have a program to build prostheses and really to build a whole prosthetic sector in areas of the world that historically do not have access to prostheses. So we're in Western Africa and Sierra Leone, and we're actually building an entire sector to distribute prostheses to victims of the Civil War there.
Okay, well, we've run out of time, but I'm going to ask you a question. Maybe just one missing piece for your research. If you had to just think about one thing that would help, it could be funding, it could be collaborating, it could be data, it could be scale up. What is that missing piece that could help your research the most?
Looking at me first.
Okay, well, time stop.
So I think for us, it's having the flexible funding to run quickly, because I think that the example that wasn't a very quick example is flexible funding to run quickly. We have the most brilliant researchers, students, graduate students, postdocs in the world here, all working together. And we have the ability to invent and move quickly and transition to the clinic. And so in my lab, and that's the limiting step.
I would say funding and people, not just the funding, but to be able to, we have these brilliant minds and we can leverage what we're doing with more people working for us, more people working with us. So funding translates to a larger set of people working on these questions.
Yeah, I just echo that, funding and people. So academia is very, very optimized for creating the next generation of young scientists. It's very optimized for generating knowledge. But I think we could do a better job in generating therapeutics at a rapid pace. And to do that, we need to build human communities within MIT that are very, very diverse, that span a vast age range. So we need to link people with gray hair that has 40 years experience in some material or power supplies or whatever it may be, and link those people with very young, agile minds. And by doing so, we'll be unstoppable in our ability to rapidly innovate.
Yeah, I echo funding and people, and I think we need you. We really need you to go and tell everybody that you're going to talk to in the next week about all of the amazing things that are happening here, and how we are really trying to solve the problem that many people are suffering from. Right? This academia is not some like ivory tower where we're working on things that only support us. These are problems that impact everyone. Somebody in your lifetime has had TB or cancer or a terrible accident. So what I need everybody to do, in addition to thinking about getting us great people, thinking about getting us funding, go and tell at least 20 people, 20, about the amazing things that you heard about, and you're going to hear about it in the next few days. And when everybody says, what do they do over there? They help you.
So that brings us to the conclusion of this panel. So first of all, thank you to all of our wonderful panelists. So again, round of applause. And huge thanks to the MIT alums here in the auditorium, but also streaming from around the world. Amazing questions. Unfortunately, we couldn't get through all of them. And we're going to take a short break, and we'll be back for a second segment with Mythic and a fireside chat with President Sally Cornwell. So thank you very much.
Our program will continue after a short break.